Hello everyone, we are starting the topic of MOSFETs or metal oxide semiconductor field effect transistors. We are going to look at MOSFET types and the IV characteristics of the MOSFETs. MOSFETs, like BJT transistors, have two applications. They are used as amplifiers or as switches, for example, in the implementation of digital gates. In this course, we're going to study both applications of MOSFETs. When they're used as amplifiers, they can amplify signals with small amplitude and generate signals with larger amplitude at the output. And because of their functionality as a switch, they are used in implementation of digital gates. We are going to study how to use MOS transistors in implementing digital gates in this course. Here are the cross-section of NMOS and PMOS transistors, as well as a 3D picture of an NMOS transistor. So this is our NMOS and this is our PMOS transistor, and this is the 3D picture of an NMOS transistor. In an NMOS transistor, the substrate is made using a P-type semiconductor, and there are two wells built using N-type semiconductor. In a P-type MOSFET, the substrate is N-type and the wells are P-type semiconductors. So both of them have four terminals: gate, drain, source, and body. The same goes for a PMOS transistor. If you look at a 3D picture of an NMOS transistor, this is the length of the channel is shown by letter L, and this is the width of the channel. The length of the channel in MOSFET transistors is the minimum feature size. In other words, the width of the channel is much longer than the length of the channel. And as you saw in the introduction video, there is an oxide layer between gate and substrate. The thickness of this oxide layer is shown with T oxide, and the capacitance of this oxide layer is shown with C ox. The first region of operation of an NMOS transistor that we are going to study is the cutoff region. In the cutoff region, there is no inversion layer generated under the gate, so there is no channel under the gate for NMOS transistor. As a result, there is no path for the current to flow from drain to source. This happens when the gate to source voltage is less than a parameter called threshold voltage of an NMOS. This stands for threshold and N stands for the NMOS, the type of the transistor. Threshold voltage is a parameter of a MOSFET transistor, and the value of it is going to be given in the datasheet for any specific transistor. In this course, we're always going to assume that the substrate is connected to the source, and the voltage difference between gate and substrate is the same as the voltage difference between gate and source. To be able to induce an inversion layer under the gate or generate a channel in the MOSFET transistor, the value of VGS must be greater than threshold voltage of the transistor. So for VGS values less than VTN, no channel will be induced and no current will flow. There is an important terminology in the MOSFET transistors, and that is overdrive voltage. V overdrive is defined as the difference between VGS and V threshold of the MOSFET. So V overdrive for an NMOS transistor is VGS minus VTN. In the cutoff region, V overdrive is less than 0. Let's see what happens if we increase the value of VGS beyond V threshold. For VGS values greater than V threshold of NMOS, there is going to be a channel induced under the gate. And if we apply small voltage to the drain with respect to the source, then the current that flows from drain to source is going to be equal to this expression. And the magnitude of this current, the drain current, is controlled by the magnitude of the voltage that's applied to the gate. This quantity here, VGS minus VTN, is the same as V overdrive by definition. So these two are the same equations. So we apply the gate to source voltage greater than threshold voltage of the NMOS and apply the small voltage to the drain of this transistor, and this is our current that flows from drain to the source. Now for small VDS values, the MOSFET is going to act like a resistor, because if you look at the equation, ID versus VDS has the same IV equation of a resistor, and the conductance of this transistor can be calculated using this expression. Let's see what happens if the value of VDS is increased. As VDS is increased, the channel becomes narrower near the drain. As a result, the current equation that we are going to use for larger VDS values is provided here. If you look at this expression for small VDS values, this current equation is similar to the one that we had in the previous section. For small VDS values, we can discard this term here, and these two equations are similar. This region of operation of MOSFET is called triode region. Let's move on and see what happens if the value of VDS is increased even more. When VDS is increased further such that VDS is equal to V over drive, the channel depth becomes 0 at the drain. At this point, we're going to say that the channel is pinched off and the transistor enters the saturation region. The equation for the drain current in the saturation region is provided here. After this point, if the VDS is increased furthermore, the current cannot change and the amplitude of the current is going to stay constant for a constant VGS value. Here is the IV curve of an NMOS for a given VGS or a constant V over drive value. For small VDS values, we are at this region. The IV curve looks like a straight line. As you increase VDS, the curve is going to bend, but for the entire region, the transistor operates in the triode mode, and you can use the ID equation in the triode region. After VDS reaches V over drive value, for VDS values greater than V over drive, the transistor enters the saturation mode and you have a different ID current for the saturation mode. As before, VGS equals to V threshold plus V over drive. This curve is for one VGS value. Let's look at IV curves of NMOS transistors for different VGS values. Here they are. You have different curves for different VGS values. As you increase VGS value, the current is also going to increase. Again, for this range, when the value of VDS is less than V over drive, the transistor operates in the triode region, and when the value of VDS is greater than V over drive, the transistor operates in the saturation region. VDS equals to V over drive is called the edge of saturation. For VGS values less than a threshold voltage, and the transistor is going to be in the cutoff region. MOSFETs have another feature called channel length modulation, and that is, as VDS increases beyond V over drive, this pinch off point moves away from the drain. This phenomenon is called channel length modulation, and because the channel length decreases, the drain current is going to increase. To take that effect into account, the drain current is revised to this equation. So in the saturation region, the effect of VDS is taken into account for the calculating the drain current. These curves on this graph show the effect of the channel length modulation on the drain current. If you extend the lines of drain current, they're going to coincide at one point. VDS at that point is equal to negative VA. This is early voltage, and that is equal to 1 over lambda. Lambda is called the channel length modulation parameter. Let's take a look at the circuit symbols for NMOS and PMOS transistors. All three of these symbols represent an NMOS, and these three symbols represent a PMOS transistor. In general, these MOSFETs are 4-terminal devices: source, gate, drain, and body. Source and body are usually connected to each other. As a result, we can represent them with only 3 terminals. In this course, we are going to use these 2 symbols for an NMOS and PMOS transistor. We have 3 terminals: gate, drain, and source for the case of an NMOS transistor, and 3 terminals for the case of a PMOS transistor. In both NMOS and PMOS transistors, the arrow is on the source terminal, And for the case of PMOS, this arrow points inside the device. For the case of an NMOS transistor, the arrow points outside of the device. In an NMOS transistor, a current flows from drain to source. We're going to show it with I sub D, or the drain current, but ID and IS are the same. And for the case of PMOS transistor, the current is going to flow from source to the drain. So again, we are going to represent that current with I sub D, but I sub D and IS are the same. Let's look at the labeling of the voltages for both NMOS and PMOS transistors. The gate to source voltage in an NMOS transistor, we're going to represent it with VGS. Drain to source voltage, we're going to show it with V sub DS. And this is again I drain. Because there's an insulator layer between the gate and substrate, I gate is equal to 0, so there's no current flowing from gate to the substrate. For the case of PMOS, we are going to switch the subscript of the voltages. In other words, we are going to label the source to drain voltage as VSD and the source to gate voltage as VSG. Again, no current flows from the gate to the substrate in a PMOS transistor. ID or IS flows from source to the drain. Here is a summary of IV equations for the case of PMOS and NMOS transistor. They are similar, with the only difference that we switch the subscript for the node voltages in the PMOS compared to an NMOS transistor. Looking at the NMOS equations, V overdrive by definition is VGS minus V threshold of NMOS. If it is in the cutoff region, V overdrive is less than 0 and ID is equal to 0. When NMOS operates in the triad region, V overdrive is greater than or equal to 0, but VDS is less than V overdrive voltage. Here is the current equation for that region of operation. When the transistor operates in the saturation region, V overdrive is greater than or equal to 0 and VDS is greater than V overdrive voltage. And we're going to use this equation, current equation, for that region. For the case of PMOS transistor, V overdrive is defined as VSG minus V threshold of PMOS transistor. Again, we are using VSG instead of VGS for the case of PMOS. Also, because the threshold voltage has a negative value for a PMOS transistor, we're going to use it in an absolute value. Just like an NMOS transistor, when PMOS is in cutoff, V overdrive is less than 0 and drain current is equal to 0. When it operates in this triad region, V overdrive is greater than or equal to 0 and source to drain voltage is less than V overdrive. This is the current equation for that region. When the transistor operates in the saturation region, V overdrive is greater than or equal to 0 and the source to drain voltage exceeds the overdrive voltage. And here is the equation for that region. In summary, today we looked at MOSFET transistor, their structure and modes of operation, and their IV characteristics. Thank you for watching.